A while ago, I had the opportunity to sit in on an appointment with a doctor and a patient, and after the patient left, the doctor made some notes and made reference to the patient responded with a first order response. And I'm like thinking to myself, what does a first order response mean? In this video clip, we're going to talk about the concept of the response order. What is the order of a reaction with respect to a specific reactant? And we're going to use a medical dosage example to illustrate the point. Now, this video is going to probably be longer than some of the others. This is an introductory video, and you'll be referring to these concepts all throughout the unit on chemical kinetics. So I want you to have this scenario in mind. We have a patient who has a headache, and that person takes one aspirin. And one aspirin, and the response time is 1 hour. Okay. So now you would expect that if the patient takes 2 aspirin, then the response time would be twice as fast, or a half hour. And that's the example of a first order response. A first order response is an expected response, and the response time would be 1/2 hour. Now, a zero order response would mean that there's no difference. The patient takes double the medication, but the response time is exactly the same. And so that would be a case over here where there's no effect to aspirin, and the response time remains as 1 hour. But then there are situations where a patient may respond to medication in a second order manner, and a second order will be kind of doubly effective over here. So I'm going to refer to this as loosely as doubly effective, and the patient takes 2 aspirin, and the response time is 1/4 of an hour. Now, the order is the order of the response. So for example, a first order means that we have 1/2 to the first power. That's the first order. A second order would mean that we have 1/2 to the second power. That's the order of the reaction. And a zero order would be equal to 1/2 to the 0 power, right? 0 power. And anything raised to the 0 power is 1. Now, if we were to graph the dosage response, let's start with the expected response. Let's say that we have 100 milligrams in the system, that we're going to graph the concentration of the aspirin versus time. And these will be, for example, 1 hour, 2 hours, 3 hours, 4 hours, 5 hours. Well, if we start off with 100%, and then let's say the half-life is 1 hour, then after 1 hour we would have 50% remaining. And then after another hour, we would have half of that half, or 25% remaining. And then after another hour, the third hour, we would have 12.5% remaining, and so forth. Then 6%, 3%, and our response curve would look like this. And I want to make a note over here that we have a consistent half-life. If the half-life, and again, this is an example, not all half-lives are 1 hour, but we have a consistent half-life. Now, something that is doubly effective or second order, that medication is medication is lasting longer than you would expect. It's not degrading as fast as you would expect. And the example, this graph would look like the following. Here's concentration of aspirin versus time, and at time 0, let's say that we have 100 milligrams of the medication, and then let's say for the sake of argument, after 1 hour we have 50%. But then the half-life keeps doubling. The consecutive half-lives double. So if the first half-life is 1 hour, the next half-life would be 2 hours, or in other words, so 2 hours, and it would take 2 hours to get to the next half, the 25%. And then we had 1 hour, then 2 hours, then 4 hours, right? 1, 2, 3, 4 hours. So that would be over 7 right there. And that we would take that long to get to the 12.5%. And then, so this was a half-life of 1 hour, a half-life of 2 hours, a half-life of 4 hours, and now we would have the next half-life would be a half-life of 8 hours. So 8 hours, 8 plus the 7, 8, 9, 10, 11, 12, 13, 14, 15. And at that point, that's where you'd have 6.25%. I'm writing really small. So our response curve would look like this. And backtracking, if we have a zero order means that you give the medication to the patient and it just degrades. There's no half-life. So actually, let me back up here. Here, the consecutive half-lives double. So half-life doubles consecutively, meaning that every subsequent half-life keeps on getting double the first one. And in a zero order, there is no half-life. So let's say we start off with medication, and then after 1 hour it goes down, and then after another hour it goes down, and then after another hour it goes down, and we would get a line, a straight line. And so this is going to be a straight line. Now, we want to analyze medication responses, and scientists love to have lines. We want to have a line so that we can have intersection points between, imagine a patient is taking multiple medications. What's the response with one medication? What's the response for another one? And what is the ideal dosage that you would give to that patient of the different medications? Maybe they're taking something for arthritis, another thing for a blood thinner, and so forth. So this is where the mathematicians come into play. We are going to replot this graph, but instead of plotting concentration versus time, we're going to plot natural log of concentration versus time. Natural log of the concentration versus time. And if we were to plot those points, that would end up converting this hyperbolic graph into a line. And the line, it would look something like this. And so that's how we convert it to a straight line. Now, the slope of this line is going to be indicative of it's going to be equal to what's called the rate constant. If the slope is a greater slope or more pronounced, that means the medication is reacting really fast. But if it's a low slope, then it's taking longer. So this slope is going to be equal to the rate constant, but it's a negative slope. So this is going to be negative K, or negative rate constant. Let's go to the second order graph. In the second order graph, again, this is where the mathematicians come into play. We are going to replot this data, but instead of plotting concentration versus time, this time we're going to plot the reciprocal of the concentration versus time. And when we plot those data points, that converts this curve into a line with a positive slope. And so the slope over here, again, is going to be equal to the rate constant, but it's a positive slope. So this is just going to be equal to K, our rate constant. And going back to the zero order graph, the zero order graph is already a straight line. So this slope right here, and it's a negative slope, so this is going to be negative K, or rate constant. And now let's put this all together and write down what's called the integrated rate law equation for each of these responses. starting with the zero order, you'll remember from algebra class in maybe, what, 7th, 8th, 9th grade or so, the equation for a line is generally reported as y equals mx plus b, where y is the y-axis values, m is the slope, and x is the x-axis, and b is the y-intercept. So y, concentration of A, equals the slope, m is the slope, negative k, x, which is time, and then the y-intercept would be the original concentration, and this would be what they call the integrated rate law equation, which we're going to use in subsequent problems over here for zero order. For a first order response, y equals mx plus b, y is the y-axis, natural log of A. The slope, again, is the rate constant, and it's a negative slope here, so negative k times time plus the y-intercept, and the y-intercept is going to be the natural log of the original concentration of the aspirin or the reactant. And that's our first order integrated rate law. And then our second order integrated rate law, again, once again, y equals mx plus b, y is 1 over A, m is the slope, but this is a positive slope, so that's k, times t, time, plus 1 over the original concentration of the aspirin. The brackets means concentration. So this video is a pretty dense video here. We have the concept of the response of the order. We have first order, second order, and zero order. We will learn subsequently that there are other orders, half order and third order, but this is the basic concept.